GIS Fundamentals, Section 6, Aerial and Satellite Images. Remotely sensed data come in many forms. However, in the context of GIS, we usually use the term to describe aerial images taken from aircraft using film or digital cameras, or satellite images recorded with satellite scanners. Remotely sensed images are valuable sources of spatial data for many reasons, including large area coverage. Images capture data from large areas at relatively low cost and in a uniform manner. Extended spectral range. Photos and scanners can detect light from wavelengths outside the range of human eyesight. Geometric accuracy. Remotely sensed data may be converted to geometrically accurate spatial data. Permanent record. An image is fixed in time, so conditions at the time of the photograph may be analyzed many years hence. Remotely sensed images are valuable sources of spatial data because they provide large area coverage, extended spectral range, geometric accuracy, and permanent record. Basic principles. The most common forms of remote sensing are based on reflected electromagnetic energy. When energy from the sun or another source strikes an object, a portion of the energy is reflected. Different materials reflect different amounts of incoming energy, and this differential reflectance gives objects a distinct appearance. We use these differences to distinguish among objects. Light energy is characterized by its wavelength, the distance between peaks in the electromagnetic spectrum. Each color of light has a distinctive wavelength. For example, we perceive light with wavelengths between 0.4 and 0.5 micrometers as blue. Light emitted by the sun is composed of several different wavelengths, and the full range of wavelengths is called the electromagnetic spectrum. X-rays have wavelengths approximately 0.0001 micrometers. Visible light is between 0.4 and 0.7 micrometers, and near-infrared light is between 0.7 and 1.1 micrometers. We typically identify three base colors: blue from 0.4 to 0.5 micrometers, green from 0.5 to 0.6 micrometers, and red from 0.6 to 0.7 micrometers. Electromagnetic energy striking an object is reflected, absorbed, or transmitted. Most solid objects absorb or reflect incident electromagnetic energy and transmit none. Liquid water and atmospheric gases are the most common natural materials that transmit light energy as well as absorb and reflect it. Energy transmittance through the atmosphere is most closely tied to the amount of water vapor in the air. Water vapor absorbs energy in several portions of the spectrum, and higher atmospheric water content results in lower transmittance. Natural objects appear to be the color they most reflect. For example, green leaves absorb more red and blue light and reflect more green light. Most remote sensing systems are passive, in that they use energy generated by the sun and reflected off the target objects. Aerial images and most satellite data are collected using passive systems. Most passive systems are not useful during cloudy or extremely hazy periods because nearly all the energy is scattered and no directly reflected energy may reach the sensor. Most passive systems rely on the sun's energy, so they have limited use at night. Active systems generate an energy signal and detect the energy returned. Differences in the quantity and direction of the returned energy are used to identify the type and properties of features in an image. Radar, radio detection and ranging, is the most common active remote sensing system, while the use of LiDAR systems, light detection and ranging, is increasing. Radar focuses a beam of energy through an antenna and then records the reflected energy. These signals are swept across the landscape, and the returns are assembled to produce a radar image. Because a given radar system is typically restricted to one wavelength, radar images are usually monochromatic, or in shades of gray. These images may be collected day or night, and most radar systems penetrate clouds because water vapor does not absorb the relatively long radar wavelengths. Aerial images. Photogrammetry, the science of measuring geometry from images. Although there are hundreds of applications for aerial images, most applications in support of GIS may be placed into three main categories. First, aerial images are often used as a basis for mapping to measure and identify the horizontal and vertical locations of objects. Second, image interpretation may be used to categorize or assign attributes to surface features. Third, images are often used as a backdrop for maps or other features, as when photographs are used as a background layer for survey maps produced by the U.S. National Resource Conservation Service. Camera aircraft formats and systems. Aerial camera systems are most often specifically designed for mapping, so the camera and components are built to minimize geometric distortion and maximize image quality. Mapping cameras have features to reduce image blur due to aircraft motion, enhancing image quality. They maintain or record orientation angles so distortions can be minimized. These camera systems are precisely made, sophisticated, highly specialized, expensive, and images suitable for accurate mapping are rarely collected with non-mapping cameras. A simple camera consists of a lens and a body. The lens is typically made of several individual glass elements with a diaphragm or other mechanism to control the amount of light reaching the sensing media, the digital sensor or film that records light. These sensors have a characteristic dimension, and for digital sensors, a pixel size that, when combined with the flying height and focal length, determine the ground resolution and imaged area. An exposure control, such as a shutter within the lens, controls the length of time the film is exposed to light. Cameras also have an optical axis, defined by the lens and lens mount. The optical axis is the central direction of the incoming image, and it is precisely oriented to intersect the sensor in a perpendicular direction. Images are recorded on a flat stage called the camera's focal plane, perpendicular to the optical axis. Image scale, and as in map scale, is defined as the relative distance on the image to the corresponding distance on the ground. Image extent is the area covered by an image and depends on the physical size of the sensing area or element, the camera focal length, and the flying height. Image resolution is the smallest object that can be reliably be detected on the image. Resolution in digital cameras is often set by the pixel size. Digital area cameras. The lens focuses light onto charged coupled devices, CCDs, or similar electronic scanning elements. A charged coupled device is a rectangular array of pixels or picture elements that respond to light. Digital cameras sometimes use a multi-lens cluster rather than a single lens, or they may split the beam of incoming light via a prism, diffraction grating, or some other mechanism. Since charged coupling devices are typically configured to be sensitive to only a narrow band of light, multiple charged coupling devices may be used, each with a dedicated lens and specific waveband. Film and film cameras. Cameras capable of using 240mm film are considered large format, while smaller sizes, for example 70mm, were once common. Large format cameras are most often used to take photographs for spatial data development. Film consists of a sandwich of light-sensitive coatings spread on a thin plastic sheet. These layers, referred to as emulsions, undergo chemical reactions when exposed to light. Black and white films are sensitive to light in the visible portion of the spectrum, from 0.4 to 0.7 micrometers, and are often referred to as panchromatic films. True color film is also sensitive to light across the visible spectrum, but in 3 separate colors. Geometric quality of aerial images. Most aerial images contain geometric distortion. Most geometrically precise maps are orthographic. An orthographic map plots the position of objects after they have been projected onto a common plane, often called a datum plane. Objects above or below the plane are vertically projected down or up onto the horizontal plane. Unfortunately, most aerial images provide a non-orthographic perspective view. Perspective views give a geometrically distorted image of the Earth's surface. Distortion affects the relative positions of objects, and uncorrected data derived from aerial images may not directly overlay data in an accurate orthographic map. Distortion in aerial images comes primarily from 6 sources: terrain, camera tilt, film deformation, the camera lens, sensor defects or other camera errors, and atmospheric bending. The first 2 sources of error, terrain variation and camera tilt, are usually the largest sources of geometric distortion when using an aerial mapping camera. The last four are relatively minor when a mapping camera is used, but they may still be unacceptable, particularly when the highest quality data are required. Terrain and tilt distortion in aerial images. Terrain variation, defined as differences in elevation within the image area, is often the largest source of geometric distortion in aerial images. Terrain variation causes relief displacement, defined as the radial displacement of objects that are at different elevations. The nadir point is directly below the camera. Terrain distortions are radial. Higher elevations are displaced outward, and lower elevations displaced inward relative to the center point. Relief distortions affect angles and distances on an image. Scale is not constant on aerial images. A vertical aerial image taken over varied terrain is not orthographic. Camera tilt, in which the optical axis points at a non-vertical angle, results in complex perspective convergence on aerial images. Objects farther away appear to be closer together than equivocantly spaced objects that are nearer the observer. Tilt distortion is zero in vertical photographs and increases as tilt increases. Perspective distortion caused by tilt is somewhat difficult to remove, and removal tends to reduce resolution near the edges of the image. Therefore, efforts are made to minimize tilt distortion by maintaining a vertical optical axis when images are collected. System errors: media, lens, and camera distortion. Radial lens displacement is one form of distortion commonly caused by the camera system. Whenever a lens is manufactured, there are always some imperfections in the curved shapes of the lens surfaces. These cause a radial displacement, either inward or outward, from the true image location. A radial displacement curve is often developed for a mapping camera lens, and this curve may be used to correct radial displacement errors when the highest mapping accuracy is required. Stereophotographic coverage. If two overlapping photographs are taken, called a stereo pair, then these photographs may be used together to determine the relative elevation differences. Relief displacement in a stereo pair may be used to determine elevation and remove distortion. Many mapping projects collect stereophotographic coverage in which sequential photographs in a flight line overlap, called endlap, and adjacent flight lines overlap, called sidelap. A stereo model is a three-dimensional perception of terrain or other objects that we see when viewing a stereo pair. As each eye looks at a different adjacent photograph from the overlapping stereo pair, we observe a set of parallax differences, and our brain may convert these to a perception of depth. Stereo viewing creates a three-dimensional stereo model of terrain heights, with our left eye looking at the left photo and our right eye looking at the right photo. The three-dimensional stereo model can be projected onto a flat surface and the image used to digitize a map. We may also interpret the relative terrain heights on this three-dimensional surface and thereby estimate elevation wherever we have stereo coverage. We can use stereo pairs to draw contour lines or mark spot heights. This has historically been the most common method for determining elevation over areas larger than a few hundred hectares. Stereo models are visible in stereo pairs due to parallax, a shift in relief displacement due to a shift in observer location. The displacement of any given point is different on the left versus the right ground views because the relative viewing geometry is different. Points are shifted by different amounts, and the magnitude of the shift depends on the distance from the observer or camera to the objects. This shift in position with a shift in viewing location is by definition the parallax and is the basis of depth perception. Geometric correction of aerial images. Uncorrected aerial images should not be used directly as a basis for spatial data collection under most circumstances. Photogrammetry provides the tools needed to remove geometric distortions from photographs. These corrections depend on two primary sets of measurements. First, the location of each image's perspective center or focal center must be known. This is approximately the location of the camera focal point at the time of imaging. It can be determined from precise GNSS or deduced from ground measurements. Second, some direct or indirect measurement of terrain heights must be collected. Armed with perspective center and height measurements, we may correct our aerial images. Geometric correction of aerial images involves calculating the distortion at each point and shifting the image location to the correct orthographic position. Digital orthophotographs are most often produced using a soft copy photogrammetric workstation. Soft copy photogrammetry uses mathematical models of photogeometry to remove tilt, terrain, camera, atmospheric, and other distortions from digital images. Control points are identified on sets of photographs, stereo models developed, and geometric distortions are estimated. These distortions are then removed, creating an orthophotograph. These orthographic images, also known as orthophotographs or digital orthographic images, have the positive attributes of photographs with their rich detail and timely coverage, and some of the positive attributes of cartometric maps, such as uniform scale and true geometry. Multiple images or image strips may be analyzed, corrected, and stitched together into a single mosaic. Photo interpretation. A photo or image interpretation is the process of converting images into information. Interpreters use the size, shape, color, brightness, texture, and relative and absolute location of features to interpret images. This ground truth is invaluable in developing the local knowledge required for accurate image interpretation. When possible, ground visits should take place contemporaneously with the photographs. Photo interpretation most often results in a categorical or thematic map. Identified features are assigned to one of a set of discrete classes. Photo interpretation requires we establish a target set of categories for interpreted features. Photo interpretation also requires we establish a minimum mapping unit, or MMU. A minimum mapping unit defines the lower limit on what we consider significant and usually defines the area, length, and/or width of the smallest important feature. Satellite images. Satellite images are similar to aerial images when used in a GIS. However, there are important differences between photographic and satellite-based scanning systems. Satellite scanners have several advantages relative to aerial imaging systems. Satellite scanners also have a very high perspective, which significantly reduces terrain-caused distortion. Because satellites are flying above the atmosphere, their pointing direction, or attitude control, is very precise, and so they can be maintained in an almost perfect vertical orientation. There may be a number of disadvantages in choosing satellite images instead of aerial images. Satellite images typically cover large areas. So, if the area of interest is small, costs may be needlessly high. Satellite images may require specialized image processing software. Acquisition of aerial images may be more flexible because a pilot can fly on short notice. Many aerial images have better effective resolution than satellite images. Finally, aerial images are often available at reduced costs from government sources. Basic principles of satellite image scanners. Scanners operate by pointing the detectors at the area to be imaged. Each detector has an instantaneous field of view, or IFOV, that corresponds to the size of the area viewed by each detector. This instantaneous field of view may be thought of as approximately equal to the raster cell size for the acquired image. The scanner builds a two-dimensional image of the surface by pointing a detector or detectors at each cell and recording the reflected energy. Data are typically collected in the across track direction, perpendicular to the flight path of the satellite, and in the along track direction, parallel to the direction of travel. Some older designs use a spot detector and a system of mirrors and lenses to sweep the spot across the track. Other designs have a linear array of detectors, a line of detectors in the across track direction. Finally, a two-dimensional array may be used, consisting of a rectangular array of detectors. Because most satellites are in near-polar orbits, images overlap most near the poles. Adjacent images typically overlap a small amount near the equator. High-resolution satellite systems. Commercial systems providing 30 centimeter resolution are in operation. Satellite data are attractive when collecting data for larger areas. Aerial images may be preferred when resolutions of a few centimeters are needed. Aerial images will not be completely replaced by satellites, but they may well be pushed towards the finest resolutions and county-sized or smaller collections. The WorldView 3 satellite currently provides the highest resolution available on a global basis, with a maximum resolution of 31 centimeters provided as panchromatic images. Pleiades 1 and 2 were launched in late 2011 and 2012 by the European Consortium. Another set of high-resolution images come from the Système pour Observation de la Terre SPOT, versions SPOT 6 and SPOT 7. SPOT is one of the longest-running uninterrupted satellite imaging systems. The French government led the development of the SPOT satellite system. Landsat. The Landsat 8 satellite is the latest and the longest-running series of intermediate resolution imaging satellites. Aerial images are typically less expensive for small areas. Large-scale aerial images are often available from government sources at low cost. Each photograph covers from tens to hundreds of square kilometers, with low cost per square kilometer. As the size of the study area increases, the costs of using aerial photographs may increase. Satellites, because of their high view and larger aerial coverage, are less likely to require the creation of mosaics and may have significantly less terrain distortion, important for larger areas. Satellite scanners may detect well beyond the visible and near-infrared portions more common in aerial scanners. Airborne LiDAR. A number of laser-based light detection and ranging systems, or LiDAR, are becoming common. Lasers are pointed at the Earth's surface from an aerial or satellite platform. Pulses of laser light emitted, and the reflected energy is recorded. Like radar, laser systems are active because they provide the energy that is sensed. Unlike radar, lasers have limited ability to penetrate clouds, smoke, or haze. LiDAR systems have been used primarily to gather data about topography, vegetation, and water quality. Laser pulses reflect back from the canopy and the ground, and the strength and timing of the return is used to estimate ground height, canopy height, and other canopy characteristics. LiDAR signals over water also typically result in multiple returns, including water surface height and from various depths. So lasers may be used to measure water clarity and nearshore water depth. Discrete return LiDAR is most common, wherein the system records specific values for each laser pulse downward. Discrete return LiDAR systems produce point clouds consisting of X, Y, and Z coordinates. And the intensity, scan angle, return order, and other information. Modern laser systems often produce densities of several to tens of points per square meter of ground area, and these point clouds must be processed to remove errors, identify ground points, and assign points to feature types such as buildings or vegetation. Ground resolutions of 10 centimeters or better are currently possible when LiDAR is combined with precise GNSS and aircraft orientation measurements. There is a standard LAS format maintained by the American Society of Photogrammetry and Remote Sensing, ASPRS. The standard defines the file structure, content, storage order, naming, codes, and all other information so that any user may be able to access, process, and distribute LiDAR data in a standard way. The standard has evolved through various versions up to 1.3. The convention defines the standard LiDAR exchange file with a .las file extension Image sources. The National Agricultural Imagery Program, NAIP, provides coverage of much of the lower 48 United States on an annual basis. The USGS and U.S. Forestry Service routinely take aerial images for specialized purposes. The USGS uses aerial images in the development of digital orthophotographs and maps. Current Landsat data are available through NASA and the USGS. SPOT, Iconos, QuickBird, and other satellite system data may be obtained directly from the managing sources.